We chose a door dampener. A door dampener is commonly used to close doors without allowing them to hit the frame hard enough to cause damage. Their forms can range from a 3-bar mechanism to a 5 or 6. The chosen one for the project is a 4-bar design found adjacent to the class's lecture hall. In this report, the mechanical ability of the door dampener is explored using graphical, vector loop, and Newton-Raphson method analysis, as well as computer simulation. The door dampener had leg lengths of 11.375 inches, 9.75 inches, 10.5 inches, and 11 inches. And we use 60 degrees and 110 degrees for theta 2, and our assumed angular velocity is 0.5 radians a second, and angular acceleration is 1 radian per second squared. The position of the system can be worked out graphically as shown. The velocity can also be worked out graphically as shown here.
Here's where we did our graphical acceleration analysis. We followed on from before, where we used the theta 2 value of 60 degrees for the first example, and we ended up finding alpha 3 value of 0.195 radians per second squared and a alpha 4 value of 1.09 radians per second squared. And then our second case, we used theta 2 equals 110 degrees, and we found an alpha 3 value of 0.226 radians per second and an alpha 4 of 0.581 radians per second squared. Shown here are all of the equations needed to find theta 3 and theta 4 using the vector loop analysis. Shown here are all of the equations needed for the velocity and acceleration vector loop analyses. On the left are the equations needed for velocity, and on the right are the equations needed for the acceleration analysis. Here is what we got after plugging in all of our given values for both examples of theta 2 equals 60 degrees and theta 2 equals 110 degrees. We found that for 60 degrees we found that our omega 3 is 0.055, omega 4 is negative 0.519, alpha 3 is 0.112, and alpha 4 is negative 1.01. Then for 110 degrees we got omega 3 is 0.646, omega 4 is 0.612, alpha 3 is negative 0.43, and alpha 4 is 1.38.
For the iterative analysis, or Newton-Raphson analysis, we calculated F1 and F2 using the two cases for theta 2 and our initial guesses for theta 3 and theta 4. Our J0, or our J matrix, was calculated using the derivative of F1 and F2 with regards to our theta 3s and theta 4s. Then we took the determinant of that J matrix, and using that J matrix, we calculated delta theta 3 and delta theta 4. Adding those to our initial guesses for theta 3 and theta 4, we recalculated F1 and F2 and used our two normal criteria of 0.0001 to determine whether or not theta 3 and theta 4 were accurate enough. You can see our initial guesses for theta 3 and theta 4 in both cases, and then our final calculated results for theta 3 and theta 4. And in addition, you can see how many iterations it took. In both cases, it took 3 iterations to find an accurate enough answer. For the velocity portion of the Newton-Raphson analysis, we took J times x dot equals v, our v vector, and we used that as, so x dot equals omega 3 and omega 4. So we took our V matrix, calculated that, and then divided by the determinant of the J matrix to get our omegas. For the acceleration portion, we found the derivative of our V matrix, and I subtracted the derivative of the J matrix by the derivative of the X matrix, which is our omega-3 and omega-4, and then we divided all of that by the determinant of the original J matrix to find alpha-3 and alpha-4, or our X double prime. You can see our results for the velocity and acceleration portion of the Newton-Raphson analysis. Again, our initial guess for theta 3 and theta 4, or our final answer for theta 3 and theta 4 are shown. And then omega 3 and omega 4, as well as alpha 3 and alpha 4 are shown in both cases.
This animation shows the path of motion that our mechanism experiences. Given that it does not complete a full cycle, it is a double rocker mechanism. We then have our results for theta being 60 degrees. Overall, our values were within a reasonable margin of error. Our graphical analysis actually ended up being more close to the exact values that we were supposed to find. The same thing applied to theta 2 equals 110. Everything was within a reasonable margin of error. The only issues we had came from the Newton-Raphson method. Overall, that still ended up working out pretty well. As far as mechanism redesign, overall our mechanism does not need much of a change applied to improve its function. The size of the two rockers could be increased to lessen the required torque needed for opening the door manually and the closing process that the mechanism goes through. However, if the size is increased too much, it could limit the mobility of the door and the mechanism itself due to the need for the door to open fully. And the mechanism itself goes through such a small range of motion that it would really not need to have Grashof criteria met for it to still work properly. For our resources used, we used a linkage mechanism designer and simulator that was mainly used to get the idea of what the motion was and to create the animation seen before. And we used our design of machinery textbook for equations and formulas.